In this video, we're going to cover Charles' law. So what Charles' law says is the volume V of a fixed mass, meaning the amount of gas is not changing, is directly proportional to its temperature T. And we are free to assume that the pressure is also constant here. So our equation for this type of a scenario where the mass of gas and the pressure are constant and the volume and temperature are the things changing is V1 divided by T1 equals V2 divided by T2. So V1 is our initial volume, T1 is our initial temperature, V2 is our final volume, and T2 is our final temperature. So as the temperature increases, so will the volume of the container. So let's look at why that is. So as temperature increases, volume also increases because as the particles heat up, we know that they are going to move faster. And as the particles move faster, it causes them to occupy more space than they did originally. Likewise, if you were to decrease the temperature, volume would also decrease because as gas particles cool down, they are going to move slower, causing them to occupy less space. It's important to note that with Charles' law and all of the laws moving forward that contain temperature, that we are going to need to plug in temperatures in Kelvin. A lot of the times we don't, in a lab setting, measure temperatures in Kelvin. We measure in Celsius because that's what our thermometers allow us to measure in. So to convert from Celsius to Kelvin, you just take your degrees Celsius and add 273 to it, and that's the temperature in Kelvin. But that's a crucial piece here, that all temperatures moving forward with gas laws have to be in Kelvin. The application of Charles' law here has to do with hot air balloons. So if you know anything about hot air balloons, it's a giant balloon and there is a heater at the bottom of the balloon. And the heater is used to heat the air inside of the balloon, causing the gas particles to move faster, which increases the volume of the balloon itself. And a larger balloon is going to displace more air, causing it to rise. And in addition to that, hot air is less dense because it's the same amount of gas, moving faster, occupying more space. And so the amount of space between particles is going to increase, which is going to lower your density. You're going to end up with less mass per volume because the particles are more spread out. And that's something that's less dense than air is naturally going to float or rise. To get a balloon to come down, a hot air balloon and a regular balloon, we would need to cool the air inside the balloon. So you typically turn the burner off, allow the gas to cool off, and that's going to cause the balloon to get smaller. It will not displace as much air. It'll start to sink. And then also that cool air is going to be less dense than the air around it, potentially, or at least less dense than what it was, causing the balloon to come down. So looking at our first example problem for Charles' law, a container containing 5 liters of gas is collected at 100 Kelvin and then allowed to expand to 20 liters. What must the new temperature be in order to maintain the same pressure as required by Charles' law? So let's start by highlighting all of our variables and let's pull them out. Our known variables, we have an initial volume of 5 liters, an initial temperature of 100 Kelvin, a final volume of 20 liters, and we are asked to find our final temperature in Kelvin. So we can literally just plug these numbers directly into Charles' law. We have our temperatures in Kelvin, so we're good to go. So I just plug the numbers in. We are going to have to cross multiply and divide to solve this. So to cross multiply and divide, we would have 5 liters times T2 is equal to 100K times 20. So we would do 100K times 20 and then divide by 5 to get T2 by itself. And we would come out with a final temperature of 400K when you plug that in. Sig fig wise, we have 3 total sig figs here, 3 total sig figs here, and 1 sig fig here. Just this one is significant. And since we're cross multiplying and dividing, we follow multiplication and division rules for sig figs, which requires us to round our answer to the total number of sig figs that is equal to the smallest total number of sig figs in our starting numbers. So since this one has 1, that's our smallest, I need to round my answer to 1 total sig fig, which is why it's 400. Let's think about whether this makes sense. So we said that these are directly proportional. So as volume increases, so does the temperature and vice versa. So we are increasing our volume, which means that our temperature should also increase, which this shows that it is. So it checks out there. But then we could also plug the 400 back in for T2 and double check that 5 divided by 100 is equal to 20 divided by 400, which it is. For example 2, we have a balloon inflated in a room at 24 degrees Celsius, has a volume of 4 liters. The balloon is heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? Highlighting our known variables here and pulling them out, we know our initial volume is 4 liters. Our initial temperature is 24 Celsius. Our final temperature is 58 Celsius. And our unknown, we're solving for V2. In this one, we are given temperatures in Celsius, but we need to convert our temperatures into Kelvin. So I'm just going to add 273 to both. And these would be our new temperatures in Kelvin. And these are what we're going to plug in to Charles' law. So I'm going to plug in V1, T1, and T2. To solve for V2, we're going to cross multiply and divide. So it's going to be 4 liters times 331K is equal to 297K times V2. So we're going to do 4 times 331 divided by 297 to get a V2 of 4.46 liters. Sig fig wise, again, multiplying and dividing would require us to round our answer to the same number of total sig figs as our starting number with the lowest amount. We have 3 total here, 3 total here, 3 total here, which is why I rounded to 3 total in my answer. Double check that this makes sense. We are increasing the temperature, which means that our volume should also be increasing, which it is, so it logically checks out. But you could also plug this in for V2 and make sure that this side of the equation equals this side, which it should. For this first check for understanding problem, I want you to hit pause, try and solve it, and then hit play when you're done. So for this one, your known values, you're given an initial volume of 6 liters, an initial temperature of 20 Celsius, and a final volume of 4 liters, and you're asked to solve for T2. You should have started by converting your temperature into Kelvin, so just add 273 to the 20 Celsius to get 293 Kelvin. And then you can plug all of your values into Charles' law, solving for T2. So you should have done 293 times 4 divided by 6 and gotten a T2 to 3 sig figs of 195 Kelvin. Feel free to keep your answers in Kelvin. You do not need to reconvert it into Celsius. Kelvin is just fine. It's the more scientific temperature scale. Pause your video here, try and solve this second check for understanding problem, and hit play when you're done. For this one, your known values, we had an initial volume of 6.8 liters, an initial temperature of 325 Celsius, and a final temperature of 25 degrees Celsius. Our unknown value, we were asked to solve for our final volume. Our temperatures were given in Celsius again, so you should have converted them into Kelvin by adding 273 to each. And then plug those along with your initial volume into Charles' law, cross multiplying and dividing. So 6.80 times 298 divided by 598 should have gotten you a final volume of 3.39 liters. And again, 3 sig figs because all of your numbers have 3 total sig figs. So your answer should also have 3. Double check that this makes sense, right? Our temperature is decreasing, so our volume should also decrease, which it shows that it is. So therefore it checks out. And that is going to be it for this video.